Welcome back. In this tutorial, we're going to look at taking an input image and then using vectors and Perlin noise to create some drawing system that's going to use the input image for the color of the pixels, but also that's going to retain some level of structure from the input image. We're also going to be talking a little bit more about this idea of texture and how we can change the quality of our drawings using some simple tweaks with the way that we're drawing our points. So this example is going to be building on the grid we created previously. So let's remix this project and let's call it Perlin Fields. And we're going to describe this as generating textures using Perlin Noise Fields and an image. Okay. All right, so we're going to keep the concept of the grid here to get started. But first, let me just delete some code here that we're not going to need for this example. So we're going to keep the grid cells here. We're going to delete this. And of course, we're going to keep using our highway image for now. Okay. Set a white stroke for the moment. So before we dive into this example, let's talk a little bit about what is a Perlin noise field and how we can expand the idea of Perlin noise we've seen so far from just a single dimension of noise to a 2D application of the noise function. So let's go into our grid here and let's draw a little rectangle. Yeah. Just to illustrate. Let's set rectangle mode center. This example, and we're going to set a black fill so we can actually see our grid. Yep. And we're going to make the grid much smaller for this example, 20. All right. So far we've seen that we can use Perlin noise with a single value. So for example, if I said let's create a color for each of those squares in the grid here using a noise value. We're going to call this gray here, just a gray value. Okay? We're going to use noise, and we're going to put in the x coordinate as the input to our noise function. Now, of course, we always need to multiply this by some amount to kind of tame it, divide it, right? Tame it down a little bit. So let's make a variable. Let's call it res. That's going to be the overall resolution of our Perlin noise here. So that's going to result in a number that's between 0 and 1. So we can use map. So I say map the noise, which is between 0 and 1. Let's map it to a number between 0 and 255. And then we are going to set the fill value to this gray level. So this is going to look something like this. So what's happening here is you can see as we're moving through the x values, right? We're using the ups and downs of the Perlin noise to set gray values. So we have kind of this smooth, continuous, but still varying gray levels. And then, of course, we could also add some kind of an offset to this by just including frame count if we wanted to, right? So that's going to sort of shift us through the Perlin space over time. But let's leave the offset for now. So there is a way that we can use noise in 2 dimensions. So if we wanted to sample here noise in 2 dimensions, right? What we would do is we would create, we could add a second parameter here. We could say y. And now by adding a second parameter, we've expanded this idea, but we've stretched it out to a grid kind of shape. Let's let's leave the stroke black so we can see a little bit better here what's happening. So in every one of these grid cells here, right? If we're using a 2D input, right, 2 values to the noise function, we can see the noise as being a 2-dimensional space. So instead of being a single line like a mountain landscape, we can think of it as terrain almost, right? So now we're looking over rolling hills. So now this has a kind of a map, 2-dimensional aspect to it. If we change the res, what's going to happen is we're kind of zooming into that space, right? Or zooming out from that space and then getting closer and closer to randomness the further away we zoom out. We could also make this interactive just for a demonstration here. In Draw, I'm going to make res, I'm going to map the mouse x coordinate of the mouse to a range of values for this res variable. So we can see how we're kind of zooming in or out of the Perlin noise space just by varying how much we're dividing. So this is a really interesting application of Perlin noise because we can use it to create, basically textures. And we can get different values at the XY points in the grid that always share the same property, which means from one of the cells, you're never going to have too big of a jump. It's always going to be a smooth transition no matter which direction you're going into. And then of course, the less we divide, the closer we get to totally random. So let's change this range a little bit here. All right, so now we can get very smooth values or denser, more busier looking grid. In fact, let's just disable the stroke altogether to see what happens. Yep. That's a nicer way of looking at it. So we can use Perlin noise using 2 values as the input, right? Kind of coordinates in a grid. And the idea we've explored so far of Perlin noise kind of moving smoothly up and down basically translates into space. And in fact, you can also do this in 3 dimensions, which means over time, you can animate these values over time by adding a 3rd parameter here. So let's say frame count times res. That's going to slowly morph these values over time if you want to by adding a 3rd parameter, which is the depth or the z coordinate. But we're not going to do this for this example. So the idea with a Perlin field is that we can kind of combine this randomly smooth generated values that we get from Perlin noise with the idea of having velocity vectors for objects. In other words, at every location in this grid, what we're going to do is we're going to create a little vector, a little arrow that's going to point in a direction according to values that we've generated from a Perlin map like this. Now, this is only giving us one value, right? One gray value for each cell. So what we're going to do is a similar strategy we've used in the past to create two values from one Perlin sample. We're just going to add an offset for the y coordinate. And if this makes no sense, let's just demonstrate it here in practice to see what that would look like. So we're going to turn this first value here, right, into the x coordinate, right, the x velocity of a vector. So let's say, let's make a vector called v. It's going to be a new p5.vector. Okay? And we'll say v.x is going to be equal to the noise value that we get at x and y in the grid. And instead of mapping it to 0 and 255, we're going to map this to -1 and 1. Okay, so that's going to be a direction. And then for the y coordinate, right, we're going to do the same thing. Now, if all we do is this, right, and I'm going to make these kind of bundled together so it's maybe a little bit easier to see what's happening. So if we do this, right, the same thing will happen as when we tried to create 2D coordinates from a single noise value, which means both of these noise functions are going to return the same number because we're giving the same input. So if we want them to be related but varied, what we're going to do is use this z parameter here, the 3rd dimension, we're going to grab the x coordinate from, let's say, 1, just arbitrarily, and then we're going to grab the y coordinate from 10, just further down the road. Okay, these numbers can really be anything as long as they're different, because we saw even the slightest little jump, right, in resolution across the Perlin noise already changes quite a bit the results we're getting. So when we do jumps of 10, you're just somewhere completely different in the noise space. So you're going to get values that are going to be different, right? But they're going to have the property of the noise, which means they vary smoothly from one position to the next. So if we combine this x and this y together, what we get is a little arrow vector. So let's represent this vector visually. So instead of a rectangle, let's set a white stroke here. And let's draw a little line. We're going to draw a line, right, from 0, 0, which remember is in the center of our grid cell, to v.x and v.y. Okay. So now what we're seeing is a whole bunch of points here. And that's because, remember, these vectors are really small. They go from -1 to 1. So if we want to see them a little bit better, we're going to cheat here. We're going to say v.mult. We're going to multiply those by a fixed amount, and in this case, we're going to use the grid size. And this is what we get. So let's make these arrows even bigger, actually, ×2, so we can see them better. So here I'm exaggerating their size here so we can see what's happening a little bit better. And remember, as I move my mouse, what happens is the res variable is being changed, right? So how quickly we're moving through the noise space, right? How smooth or how fine grain of a noise we're getting is being affected by res. So this is interesting because we're getting a similar kind of feel as that sort of cloudy texture we were getting before, except now we have these vectors at each, we can see that we can get vector coordinates anywhere on the screen, right? And they are going to have these smooth flowing lines to them because of the Perlin noise. So what we're going to do for this this demo, this example, is we're going to create a bunch of agents like we did in the previous week's videos. If you haven't watched those videos yet, by the way, now would be a good idea to do that. The ones on Perlin noise, of course, but also the ones on vectors and particle systems. We're going to create a whole bunch of vector agent objects, and we're going to set their velocity vectors, which is the direction in which they move, based on where they are on the screen. So as they make their way through this, this field here, they're going to change their direction based on Perlin noise, based on the lines formed by these vectors. And it's going to influence their motion. And we'll see, this is a nice trick to create some really intricate looking textures and compositions just using the randomness of Perlin noise. So let's see how that would translate to moving objects through that field of velocity vectors. So the first thing we'll do is create a particle system, which we've seen in the previous demos is as simple as just saying, let's make an array somewhere to be able to create our, somewhere to be able to store the particles that we're going to be creating. And then down here, we're going to make a function. We're going to call it, we're going to call this function create agent, like we did in the past. And the role of this function will be to create a little object. Let's call it temp here. And this is our object syntax. And then this object is going to contain a position. That's going to be a new P5 vector. It's going to contain a velocity. And let's just leave these two for now. And of course, this is not a semicolon, it's a colon. I always forget. All right, and then we're going to return this, this variable created by the function. I like to put this into a little function just because it makes it a little bit cleaner. Now the position of this, this agent, we're going to make it random based on the width and the height of our canvas. And oops, sorry, I meant the position, random height. Okay, so these are going to just start randomly anywhere on the screen, and the velocity we're just going to leave blank for now. So now what we're going to do is we're going to get rid of this code here. This is the code that's really showing us the grid of vectors that we can create using Perlin Noise. This is going to be the underlying system that's going to control the motion of our particles, but we don't necessarily want to draw it all the time. So what we'll do is let's take this out and let's park it for now in a function called draw noise. I'm calling it a noise field because I picture this as like a grass field viewed from the top almost. That's going to affect the motion of our agents. So let's park this to the side and let's focus on creating our agents or our particles. And eventually we're going to get them to move according to this, this noise function here. That's going to create velocities. Now we don't have to create these velocities at steps of grid, right? We can actually create this at a very fine resolution anywhere on the screen. So we don't have to use the grid framework at all here. The grid is going to be the number of pixels we have in our window. So over time, we're going to create some agents, right? We're going to say add agents over time. And we'll say group.push create agent. So that's going to give us some objects to work from. And then we're going to move and draw the agents. So let's write a for loop that's going to go through all the agents we have and then draw them. So for simplicity here, something I like to do is just grab the x coordinate and the y coordinate from the agent and just put them in a variable that has a shorter name, right? So just a temporary variable. We've done this in previous examples too. We could always refer to agent.position.x and agent.position.y, but I find it gets tedious to just type this over and over. So instead, we're just going to put them into two variables called x and y as shortcuts. And then let's see that this is moving just by drawing, this is working just by drawing a point for now at x and y. And we are going to set a white stroke so we can see them. So what we're going to see happen over time here is we're creating new agents, and these agents are getting a random position. Yeah? And they're not really moving yet. They're not moving because we did not give them a velocity, and we're also not adding the velocity to the agent's position. So let's write this code that's going to move an agent. And that just means agent.velocity, agent.position.add agent.velocity. So if we move the agents, of course, we need to give them some velocity. So the way that we can do this is we're going to use the same idea that we had over here, right? We are going to create this vector, right? A velocity vector based on their position. Now's a good time to tidy my code here. We're going to create a velocity based on Perlin noise. And in fact, we don't really need a new vector here because the agent already has a velocity. So we're going to just say agent.velocity. Oh, wait, no, let's keep it. And we're going to add this velocity to the agent's velocity vector so that it moves over time. Add v, and then let's see what that looks like. All right, so this might be a little bit hard to see here depending on the size of the screen you're watching, so I'm going to make the stroke weight a little bigger here for now so we can see them a little better. So we can see our agents now are they're moving around, right, and they're being influenced by this these vectors that are created from the Perlin noise. And if we were to draw the noise field, just to see how it's affecting it, this should be drawing it just as lines. Let's make the stroke even bigger here so we can see the agents moving. Oops, that works, but not for the noise field. So you should be able to see that they're getting pushed in directions based on where they appear and what direction these arrows are pointing towards. Now this is going a little bit intense because we are just always adding to the velocity over time. So there's no damping, right? So we can do the same as we've done before in the other examples, and then just add some damping by multiplying the velocity here by some amount a little bit, just so that things are not as crazy. And then you can kind of see here how they're moving through the field, right? They cluster and they get trapped in these little circles, right? Depending on which way the noise is pushing them, the objects are going to move in a particular direction. So their movement is completely determined by the noise function here. And in this case, the noise function applied in 2 dimension, right? And then applied twice, sampled at different places in the noise field to get an X and a Y coordinate. So we get some really interesting behavior here and patterns just from this these randomly generated noise vectors. So let's get rid of the field here. Now, one thing that's kind of typical to do with this animation is just kind of try to draw it over time. So I'm going to move the stroke down here again a little bit. And let's just draw these patterns over time to see what that looks like. And one way that we can do this is we're just going to move background here to setup. And then move it to window resized here again. So depending on a few factors here, right? Depending on the amount of damping that we have, and depending on actually, let's make the damping a variable as well. Let's call this damping. Depending on the amount of damping and the resolution, we're going to get some wildly different results here for the drawing that's being created. So for example, if we lower the resolution further, right, now we're very zoomed in on this Perlin noise field, so we get some very smooth motion, but kind of more cohesive. If we reduce the damping, it's going to be even further because now the objects are accelerating even more. Sorry, if we increase the damping, if we reduce it, the objects are now going to move much more slowly, and they have more opportunities to be affected by the noise. If we increase our resolution, like, we're going to start to see some intricate patterns that emerge from here, with lots of kind of little nooks and crannies. So it's almost reminiscent of like fur or hair or something like this. So we could add some alpha value here to our stroke. That's a nice way also to bring in some more interesting textures over time. So as the pixels overlap with each other, it increases the amount of color, or in this case whiteness, that you get. So you get a slightly more interesting image resulting from this. And again, let's compare with like basically no damping. What's going to happen is these objects are moving very, very quickly. So it creates a much more kind of chaotic looking composition. And it also takes a little bit longer for detail to emerge because we're creating one object per frame here. So we have to be a little bit patient to sort of see the image being revealed. So let's refine this example a little bit. So we're going to do a few things. First is we're going to add some code where we can add a lifespan to our agents so they're not around forever, because currently we're adding one more of these agents over time, right? They're just always there. So we're going to allow them to create shorter lines. And we are also going to remove the agents when they leave the screen so that they don't just keep drawing off screen and then slowing down our program for no reason. So we're going to clean things up here a little bit first, and then we're going to add some color to this because color is the theme of today. And we're going to use our highway image to colorize this composition. So when agents get created, not only are they going to get a position, we're also going to sample a color in the source image and then have them carry that color around, smear that color around on the canvas over their lifetime to start to kind of colorize this pattern and make it a little bit more interesting. So let's play around with this. So first, let's add a lifespan to our objects. So in our create agent function here, we're going to add a lifespan just so they're not around forever. And let's see, this is going to be maybe 512. I'm just making it up here. I need a comma at the end there. And then as we iterate through the agents here, when we move an agent, let's do it in the move agent function, we're going to reduce the lifespan by 1. And then let's write a cleanup function that's going to go through our group or a particle system and just get rid of agents that have been around for too long. So if you remember, the way that we do this is we count backwards with the index. The reason we count backwards is because as we remove objects from an array, the array itself shrinks, it gets smaller. So by starting from the end, it means that as we move back and we delete objects, the size of the array is not as important because this is where we started, -1 here, not group.length. We're going to count as long as I is equal to 0. The fact that our array is shrinking doesn't really matter because we started from the end. So if it gets shorter, it's not going to change our loop condition, right? Because we're making our way back towards 0. Sorry, it should be minus minus here, not plus plus. So we're going to start from the number of agents we have in the group. We're going to count backwards. And the reason for this is that if we find an agent, if we find that an agent's lifespan has gotten less than or equal to 0, we are going to splice this agent out of the group. Okay? So splice removes objects from an array as a reminder here. So we're going to splice this out of the group and we're counting backwards. So this means that after 512 frames, these objects are going to disappear. We could also add a condition if they leave the window, but actually in this case, I think the lifespan is enough because it guarantees they won't be around for more than 512 frames. It just means that over time, this array here, our group of agents, is not going to get out of control and just cause our whole sketch to slow down to a crawl. So let's call our code here by using cleanup group. So in draw, after we've done our animation, so now we should see some of these lines after 512 frames. They should end as we kind of get rid of some agents from the group. All right. The other thing we're going to do is now let's add the concept of colors to these agents. So whenever we want to add some attributes to the agents, we go back to our create agent function here, where we create this temporary object. So I'm going to just add one more variable in here. I'm going to call it color. And for now, maybe by default, it's going to be equal to 255. So now I can say agent.color, right, to set the color of the agent. Or what we could do is before we return this object, let's grab the actual color from this source image here, and then set that as the object's color. Now, I'm not doing it right in here because it's going to require a couple of lines of code to do that. So first, let's create the temporary object, and then we're going to assign it a color by using the object's position, right? We're going to use it to sample at that same position into the source image. And we'll need a few lines of code because we need to have some mapping here in between, because it's possible that the image, right, doesn't have the same dimensions as our canvas. So let's create SX for source X, right? So we're going to map the object's position.x, which is between 0 and width. We're going to map this to a number between 0 and image.width. And then we're going to map SY, which is position.y, between 0 and height. We're going to map it to a number between 0 and image.height. Then we can say temp.color is going to be equal to image.get, which is going to return the color at SX, SY. And then we're going to return the temporary object. So now you can see in the sketch window, now we're seeing some colorful lines. They're not just white anymore, they get some colors, and those colors are coming directly from the image that we were working with. So this highway interchange image. If you haven't seen the image, this is what it looks like, right? So it's currently taking the x coordinate of an agent, right? It's squishing it or stretching it into this image because of the map call we've done. So if we wanted this image to have the same aspect ratio, right, we would set the same aspect to our sketch window, for instance. But we don't really worry about this too much. We're only using the image as a source of colors right now. But we're also keeping some of the structure from the image because we are sampling directly where the agent gets created, where it gets first created. And then that agent will keep that color throughout its lifetime, sort of taking that point that it got at birth and then creating a streak of color through the canvas based on where it started from. So even though we can't see the original image in there, there are some elements of it that remain in the structure. So of course, if we leave this running over time, it's going to get more and more detailed. So it takes a while for the image to emerge because we're only creating one agent in every frame. So one way we could speed this up a little bit so we don't have to wait as long is we're just going to cheat a little bit here, and instead of just creating one agent over time, let's write a for loop that's going to create multiple agents in one go. So let's count from, let's say, 0 to 100. And then that means we're going to add 100 agents, right, in every frame. That's really going to speed up the drawing process quite a bit. Just, we don't have all day in this tutorial, so I just want to see some results here a little bit quicker. The other thing we might want to vary, I'm going to lower the alpha here a little bit just for my taste. Actually, I've noticed the alpha is no longer being taken into account because we're setting agent.color, so that doesn't work. We only get full alpha. So let's see if we could fix this. First here we have to be a little bit careful. So when we grab a pixel from an image, this is something that's a little bit confusing about P5.js. Let's open the developer tools here just to demonstrate. And I'm going to select my sketch here, if I can find it. There it is. So this is my image variable. Okay. So if I try to grab a color, let's call it C, I'm going to get the color at image 00. Okay. What I actually get as a result of the get function, when I extract a color from an image, I get this array of numbers here. So the same values we would get from the pixels array we looked at in previous examples. Now this is different from a color object, right? If I create a color in P5.js, what I get back is a color object that has a bunch of functions and different attributes, including the alpha value. So right now the alpha value is kind of baked into this array here, which is why it didn't work before when I set a stroke color with an alpha. So there's a few ways we could work around this. One is we could go and say, knowing that the agent color is an array of 4 values, we could say the fourth value, right, at index 3, we're going to make it equal to 25. So now we're going to see we actually now have some alpha value for our lines here, and that's going to make the drawing a little bit more interesting. And so that's one way that we can address this. The other way is just to make sure the result is a color object. So we're going to turn image.get into a color, right? So a proper P5.js color object. And now we should be able to say temp.color.set alpha to whatever alpha value we want. So that makes it maybe a little bit more explicit and more clear. It has the same effect, the same end result. The color function here will take all sorts of inputs and turn that into a color object, whether it's a string that contains RGB values, whether it's 3 separate parameters, whether it's an array of RGB values, whether it's a string that has an HTML color name or color code. It can handle a variety of things here at the input. So sometimes it's a good idea to just make sure your color values first are all turned into color objects using the color function, just to make sure it's more standardized and more uniform. Again, we don't have to put the alpha value, right? So this we're getting a very different texture or a very different feel to this drawing, depending on whether or not we use transparency or not, right? So if we don't have any transparency, we'll just get a slightly different result. So that's one thing we can address. And then just to demonstrate, we can just play with these values again a little bit. So now that we have 100 of these particles being created over time, we can see the drawing emerge a little bit more quickly. So if we change the resolution, we're going to start to see something that is going to evoke our original image almost a little bit more. If we went, very, very dense, you'll be able to recognize, some elements of the original image. So the highway interchange, I mean, it's a good source image, but that could be interesting to explore with, portraits or other maybe more descriptive images with less detail in them, so that you can see some of it translated here in the generated image. I'm just playing with the resolution here. Similarly, if we make it, really, really small, we're going to be able to create, a much completely different output. So it's worth spending some time here playing around with the dimensions and the values of res and damping. And of course, a different source image would give us a totally different color palette to work with. We can also highlight different colors by changing the background. So if I switch, for example, to a white background, now I'm kind of painting over a different canvas, so I'm going to be getting a slightly, a different result, right? It's going to make the darker colors pop more and the brighter colors become blend in a little bit more with the background, because now the background is white. For instance, we could also use one of the colors from the image as the background, for example. Okay. One thing we could do also, just to, we can play around with this concept, and, we don't have to start anywhere in the screen. We might want to say, let's create, let's create a frame, a visual frame around this composition by changing here the random values that we set when we first create the agents. So instead of fully random from 0 to width, maybe we'll set just an arbitrary border. We'll say, let's go random from 100 to width minus 100 And then we can do the same here with the height. So that's also kind of interesting to play with. It's creating almost like a mat, right, around the image we're creating, but then our particles are allowed to escape that constraint because they just get created within the zone, but then in their lifetime they can still flow out of it. Let me put the background back to black. I'm just messing around at this point with the settings here. And I'm going to increase the damping so that they move a little bit quicker. I'm going to lower the res, let's say. Actually, no. Lower the res. Too much. Somewhere in between. Okay, whatever. I like this this particular setup here. So now we can see, like, it's a bit. We start out in a kind of a sub rectangle of my drawing area, but then the particles, the agents, they can escape, right? So they can go a little bit further, and if you want them to extend even further, we could extend their lifespan, right? We could make the lifespan bigger or shorter. This way they have more time before we get rid of them, for example. So there's lots of different parameters we can play with to start to kind of influence the way this generative system is working. I'm going to go back to 512. All right. Now, the last thing I want to touch on is the idea of texture. Yeah? And already, I mean, we're creating something that's pretty textural in nature, but we can even further influence the texture of our drawing by changing the path, right? Changing how we're drawing these strokes. And sometimes, you know, you can create something by just doing less, right? Just omitting things. That's often a good strategy to start to add detail. It's kind of counterintuitive, right? But we're going to add detail by doing less. And one way that we can do this is instead of, you know, drawing a stroke like this, if we increase the alpha here for a second, just so we can see these strokes a little bit better. Notice it's creating like basically these continuous lines because of the damping value that we chose. Instead, we could create maybe like a dashed line just by saying, you know, don't draw a point in every frame. Instead, depending on where you are, right? Maybe depending on frame count or something like this, we're only going to, or maybe depending on your lifespan, only draw a point every 2 frames or every 3 frames or every 5 frames or what have you. So this is a good place that we could use modulo, right? So we could say if agent.lifespan, we're going to say modulo, let's say modulo 3 equals 0. Okay? Then we're going to draw a point. Otherwise, we're going to do nothing. And see what happens here in my drawing. Now I kind of get these dotted lines, right? That's going to add a lot of texture to the final composition. Okay, we can go even further. I'm going to put 9 here just to emphasize. So now these points, they're only drawing whenever lifespan is a multiple of 9. So they're going to move in the same way, but they're leaving way fewer dots on the canvas. This is an interesting thing to explore in your own systems. Just thinking about, you know, instead of drawing continuous line, you can play with texture just by varying how quickly those lines are being drawn. This is a strategy that, you know, artists like Jared Tarbell, for example, uses in all of his compositions, just to give them a distinct feel or a distinct style. So this almost creates kind of like a sandy texture as opposed to drawing in every frame like this. So it's all about just having a broader palette to be able to create different results and knowing, you know, what those tricks are so you can apply them to your own compositions. Let's put the alpha back in here. And we're going to leave it at that for this week's tutorials. I'm just going to let that composition here emerge for a little bit and see what the results are. And then I'll see you in the code exercise video where I'll talk about what I want you to work on for this week. All right, see you there. Okay, I'm back. By the way, so I just sped it up here. I left this example running for a few minutes, and you can see it's starting to look really intricate and really detailed. So with this idea of the Perlin noise fields, sometimes it can be interesting to just let it run for a while. Go have a snack or go eat lunch and then come back and just see what it generated. Sometimes you can be surprised at the results. All right, so I'll actually see you in the next video now.